I'm late and everyone else is. No one? Really? I'm late, right? 3. So it's homework 6, September 21. That's Monday. I have done the basics of this, but still this homework. Remember, only you have to do 3 problems out of the many ones. It might seem a little harder because I haven't been able to cover everything, but hopefully today, on how quickly I have proceeded, I might be able to give more hints. Or if you allow me, how about this? If you allow me to keep the next homework again 1 week down the line, and then I can postpone this homework by a day, then maybe you will get to see more. Do you want me to do that? Or yeah, so let's so I think it might help if I make this Wednesday, but I'll still have the next homework due at the same time, so I might be able to start over the topics. So I don't think that I'm behind too much.
So homework 7 will be due next Friday or Monday?
Monday, actually.
That's
So it's fine. Yeah. But I haven't written it down yet. I have posted it. So September 28. So let's see. Oh, the midterm, right? So that's relatively for October 9th, if I'm not wrong. And this is influx. Friday. Hopefully we can have this in class. Okay. We introduced the electrostatic potential, and basically we are doing electrostatics. And they are governed by equations that the divergence of the electric field is charge density over epsilon naught, and the curl of the electric field is equal to 0, which immediately implies that electric field can be written as the divergence of that electric potential, like that's like the force being written in terms of potential energy. But having said that, we substituted this in there. We had a strategy that first write the charge distribution or charge density, let's say, charge density rho, write an expression for that in terms of delta functions or step functions. And the second was derive the electric potential, and we said using superposition principle, we can always get this using rho of r prime divided by r minus r prime. So the point is, if this charge density was 1, then this is the electric potential due to a point charge, and that we said is a Green's function. For a point charge, we have 1 over 4 pi epsilon naught times Q over R minus R prime. Where R prime is the position of the charge. So this is integrating over that. So you basically use that superposition principle, right? You add up all the charges. And the third item is you find the electric field using the gradient of that. So that's our strategy. Given any distribution of charges, get the charge density, do this integral, and then get the electric field by taking the derivative of this. Once you have the electric field, then you can analyze the problem however you want to analyze. If you want to find the force on force or another charge, then it is Q times electric field. So that's the basic idea. So let's do a simple next is relatively complicated exercise, relatively, but it's also the simplest system you can think of, right? Let's say a charged sphere, of radius r. So we have Q, that's a circle, and the center of the circle, and let's say that's radius r of the sphere, and this is having a charge Q spread out uniformly everywhere. So uniformly charged sphere. The total charge on this is Q. Okay. What's the charge density for this? Get Q over 4 pi over 3 R cubed, right? Charge per unit of volume. But then we have to say that it's only inside the radius R, and then we say that that's given by the step function. If the radius R is greater than the observation point R, then it is contributing, otherwise it is 0. Correct? So that's our first step. Right? Identify the charge density in a reasonably mathematical manner, but that's just for, so that then you can use this in a more algebraic way. You can directly go into the second step if we know how to visualize this density. The second step is the electric potential, right? Which is a harder one because you have to do the integrals. So this is 1 over 4 pi epsilon naught E cube R prime, and that's Q over 4 pi over 3 R cube, step function R over, notice this is R prime here, so I have to replace all the R's with R primes. So this becomes R prime. And we have been using the notation that primes are all sources and unprimed quantities are observer points. That's where we are observing the electric potential. Divided by R minus R prime. Well, clearly, since it is a spherically symmetric system, it's good to work with spherical coordinates. So we have to find out what this means in spherical coordinates, magnitude of R minus R prime, and what this integral R dq R prime means in spherical coordinates. So let's specify where these coordinates. R prime is a source, so it's typically inside, right? This is inside. This is R prime. And R could be anywhere. It could be outside or inside. I could observe it inside also. So let's see. So that's fine in general. But it could be inside also. So that's an observation point. That's a source point which I have to scan all over this sphere. That's what the integral will do. And what is R minus R prime then? So let me, so this is R. I would like to know what is R minus R prime. That's equal to square root of, since it's a vector, R minus R prime dotted with R minus R prime. That's one way of defining that. That's the same as square, there's an R dotted with R, which makes it R square. R prime dotted with R prime, that makes it R prime square. That's two of the terms. But then there is also the cross terms, 2 times R dotted with R prime. That's what that is. What is R dotted with R prime? Again, we have to get into the spherical coordinates. Let's see this. So R vector and a position vector and spherical coordinates takes the form R cosine theta, no, sine theta, right? Or sine theta cosine phi in the I hat direction plus R sine theta sine phi in the j hat direction plus R cosine theta in the k hat. Right?
Shouldn't the last term in the square root be -2? Or
Yeah, this is 2. Sorry. I
it's
missed it.
minus,
Yes.
right?
And it is minus. Yeah, thank you. I don't know why my bad. Yeah. Thank you. So this is -2. I first wrote plus R dotted with R prime. This is minus. Yeah. Yes, we have math and Curtis there. Yeah, 1, 2, 3, 4. 2 of us missing. Okay. So this is -2. Thank you. Similarly, so that's R in terms of some Z axis, and let's say R prime, similarly, with respect to somewhere there is a Z axis vertically, let us say. That's another different coordinate. So this is R prime, sine theta prime, cosine of phi prime, plus R prime, sine theta prime, sine of phi prime, plus R prime cosine theta prime k hat. Okay. But still, if you were to do actually R square, so yeah, let's quickly do what is R square, right? R dotted with R is R square. If you do R square, you're going to square this, right? You dot the whole quantity. And you will notice that it is sine square theta. Then there is cosine square phi plus sine square phi, that's 1, plus cosine square theta, as R square, of course, and that's equal to R square. Right? So, because of the trigonometric identity, that works out fine. But what about R dotted with R prime? That's slightly more tricky. So that is, each of the term will have R and R prime. I multiply sine theta prime. But now there is a cosine phi and a cosine phi prime coming out. That's not simple. But not that bad. And what is the trigonometric identity for this? Cosine phi, sine phi, sin phi.
Cosine minus phi prime.
Phi minus phi prime. That's good. So let's see. R prime times, let me write that term first. This is cosine theta prime plus sine theta prime and cosine of phi minus phi prime. And it cannot be simplified further. That's the best you can go. R dot with R prime has this structure in there. But we are going to use a trick here. So this is a good exercise to find out, can we do this in general? Can we do this integral in general? And yes, it can be done, but that requires a little more machinery. We need to introduce what are legendary polynomials and spherical harmonics. But let's do a trick here. Since it's just one spherical charge we have, we can choose this to be at the origin. That's one choice we have. If you have two spheres, you don't have the choice. So if you have one sphere, you can choose this on this at the origin, and you can also use the fact that this is spherically symmetric. The whole physics is going to be spherically symmetric above this origin. So choose your z-axis along the observation point. Choose your z-axis along that observation point. You don't have that choice all the time. So this is not a general solution. Like if you have the sphere somewhere else, not at the origin, then you don't have this choice at all. If you have the z-axis along the observation point, how does this turn out to be? What changes?
Theta is 0, so this turns to 1.
Exactly. So theta is the angle between the z-axis and the observation point. So theta becomes 0. So if I choose my z-axis to be along the observation point, then my theta angle, that's equivalent to choosing theta equal to 0. So sine theta becomes 0, right? So there's a significant simplification after that. That's r prime cosine of theta prime. That's it. Right. Otherwise, it's a mess. The integrals are hard to do. But I should also say that it can be done using what is called special functions, which hopefully sometime we can do. Okay, so let's proceed with that information. So we have our integrals. I should also point out that in the same coordinate system, dq r prime is equal to r prime square r prime sine theta prime d theta prime d phi prime. That's our volume integral in here. So what's my electric potential, which is measured at the observation point, r, which is on the z-axis. I have simplified that to be on the z-axis. That's equal to 1 over 4 pi epsilon naught. Integral goes from 0 to infinity, r prime square r prime, 0 to pi sine theta prime d theta prime, and 0 to 2 pi d phi prime. Right? That's equivalent to integrating over the whole space. And my charge density is q over 4 pi by 3, or q. This is pretty much constant. It can go out of the integral all through. This is r minus r prime. And inside this we have r square plus r prime square minus 2 r prime. And it would have been the whole expression there, but this is simplified to cosine theta prime. one couldn't have proceeded if we had written the whole expression. There's one thing one can do immediately. This is equal to 0 whenever r prime is greater than r. So that means to say that whenever this is beyond that, that goes away. So I can take this to capital R. The step function pretty much does that. Remove the step function and put the limit. That's what it does. Is that clear? Like step function is 0. R minus R prime is equal to 1 when R prime is less than R, and is equal to 0 when R prime is greater than R. So it contributes only from here to up there. So, and what is this integral phi prime equal to? What is the phi prime integral? There is no phi anywhere. So it's just 2 pi. So a lot of things happening there. So let me collect whatever I can do. 1 over 4 pi epsilon naught, immediate things. So that's q over 4 pi by 3 over r cubed. And then this is 2 pi. So that's all done. So I'm left out with 2 integrals. Prime square, r prime, and okay. Let's try to do the theta integral. Whenever this kind of integral comes, notice that derivative of cosine theta is sine theta. So it is good to substitute cosine theta to be something. But in this case, we can as well substitute the whole denominator to be something. So this is r square plus r prime square minus 2 r prime cosine theta prime. Let's say that's equal to t. We are trying to do the angular integral theta prime. So these are all constant when you're taking the derivative with theta prime. That's minus 2 r prime sine theta prime d theta prime. But cosine theta has a negative sign there, so that is no negative. So that's dt. So let's do this. 2 pi and 2 pi go with a factor of 2. So this is 1 over, so this is q over 4 pi epsilon naught. And that's a factor of 3 over 2 r cubed. Integral prime. And this integral now, we have to see whenever we make a substitution, we have to change the limits and this integral. Sine theta prime d theta prime is dt over 2r over r prime. But before that, let's do the limits. When theta prime is equal to 0, theta prime is equal to 0, cosine theta prime is 1. So this is r, that is r square plus r prime square minus 2 plus or minus is equal to r plus or minus r prime square. All right, so when theta prime is equal to 0, it is a minus, and when theta prime is equal to pi, it's a plus. So this makes it r minus r prime. These are magnitudes, not vectors, square, and r plus r prime square. And whatever is remaining is dt over 2r prime, and this is square root of t. That's a relatively simple integral I can do. I can actually move this outside the integral part. So this is doing this. Right, so I just wrote it on the other side, that's all. So that this integral is doable. What is the integral of 1 over square root of t? Integral dt of this is t raised to, so it's 2 times square root of t. And then you evaluate it in the limits. So this is q over 4 pi epsilon naught, 3 over 2 r cubed. The 2 cancels the 2 that's going to come here. 0 to r. One of the r prime cancels out, which is d r prime over r. And what we have here is, this is square root of t. I have already cancelled the 2. So this is square root of r plus r prime. So maybe this is r plus r prime itself. Then minus, and when you do the lower limit, there is a slight confusion as to is it r minus r prime or r prime minus r. But remember that the square root was a way to do the magnitude. So this is actually magnitude of r minus r prime. Because we don't know which one is larger. It could be this or that. Right? So that's a small caveat to think about. Okay, that's good. Now we have to ask, where is our r? Is it outside or inside? Right? Before we go to the next integral, we have to ask, is it outside or inside? So there are 3 distances we can think of. So if you're, so there are 3 distances, r prime, and capital R, right? Surely capital R is, if r was less than r, if the observation point is inside the sphere, then we can have r comma r prime, we don't know which one, to be less than r. So it depends on the integral variable. But if you're outside, then it is very clear that r prime is less than r is greater than r, right? That's if r is outside, observation point is outside, then this is a condition. If it is inside, it could be either way. So we have to be careful in that scenario. Let's ask the harder question first, right? We are inside the sphere. So yeah. So if you're inside, so let's say r is less than r, I can split this integral into 2. So I have to go from, I'm going to break this into 2 parts. So I can go from 0 to r. Notice I'm inside the sphere. So that's r prime over r. And there is a second piece to this integral, which is going from r to capital R dr prime. Right? And there is a piece to that. I'll write that down I break this integral from 0 to r and then r to dr. If I'm going from 0 to r prime is less than r, right? This integral limit, because it's an upper limit, r prime is always less than r in this case. So that means to say that here, what I get is when it's r is greater than r prime, r cancels out. So it is 2 times r prime. That's how I got that. Maybe write that more explicitly. So this is r plus r prime minus of r is greater now. So this is r minus r prime. And the second scenario is r prime over r plus r prime. This time r is on the lower limit, so r prime is greater, so r prime cancels out, or I'm not cancelling yet, r prime. This whole thing happens if r was less than. There's another scenario, if r was greater than r, or capital R, small r, the observation point is outside the sphere, then I have to do this integral again. The integral itself is elementary, it's just the conditions that is complicating it, right? Whether you're inside or outside. If you're outside, then we don't have to worry because capital R is small, then it is sure, right? If you're outside, then observation point is always greater than the r, so we just have to do one integral. So 0 capital R d r prime over r, and this is just r plus r prime minus of r is greater, right? So it is minus of r minus r prime. Okay, so this is all for capital R. We just try to get this done, so r cancels out in this case, r prime cancels out in this case, and r cancels out in this case. And once we have r prime, we can do those integrals. That looks like a mess, but I'm doing it in various steps, so that's why it is looking long enough. It's elementary integrals. Any questions yet, by the way? Okay. So, what's our electric potential? Is equal to Q over 4 pi epsilon naught 3 over 2 r cube. By the way, before we proceed, right, what should the answer be for the electric potential inside the sphere? We know the electric field for this, right? Electric field for the, oh, I'm not being visible there, right? So the electric field for a charged sphere, we know is magnitude-wise, it keeps going straight, and this, correct? And remember, electric field is the derivative of the electric potential. Right? So derivative of, or negative derivative of the electric potential will give you this. Right? So derivative of what is linear function? In fact, negative derivative. And even if you were to get that negative derivative, it can always be off by a constant. So you can't get it exactly for any, but then electric potential is always off by a constant. Like, what's the potential energy, let's say gravitational potential on the surface of Earth? Yeah, it'll be 0, but that's a choice, right? You set your potential energy to be 0 at your 0. But in another reference, you could say, oh, that's not 0. will have some finite value. So you can always choose one point to be 0. So similarly, you'll be off by a constant, but in this way of doing it, we will actually get a constant. That's assuming that at infinity it is 0. So right away, it is not obvious to get what the electric potential is. Up to a constant you can get. This will be, if it is linear, it has to be quadratic, right? So it must be quadratic, will give you, but there's a negative of that. So it will be a parabola going down. So if you were to draw the electric potential for this configuration, there will be a parabola that goes down, right? Until the radius r. And then it is 1 over r, okay, right? So it should something go like this. This is 1 over r squared. And this is 1 over r. And this will be probably minus r squared. But then it has to be shifted up. So that's a constant that will be shifted up. So we expect those things to come up here in these integrals. So let's see how it goes. So right away we will get that. So the first integral is there is r prime, 2 r primes, and then the third r prime. So r prime, no, 2 r primes. So that's 2 plus, so 2 r prime squared divided by r. And then I will go from 0 to r. Let me do this in 2 steps. So this is 0 to r, e r prime, 2 r prime squared divided by r. That's this integral out here. And the next one is, this is 2 times r, that cancels out. So that's plus 2 times r, capital R prime, and that's just 2 r prime. This is when r is less than r. And otherwise, 2 over 4 pi epsilon naught, 3 over 2 r cubed. This is 2r prime. So that's the same integral but going from 0 to r. So I can do this integral. So it is 2 by r, and this will be r cubed by 3. Same integral going from 0. I get that integral in the second case. And this is when r is less than. Okay, let's quickly do this integrals. Elementary integrals actually. That's equal to q over 4 pi epsilon naught. There's a factor of 2 that cancels out, but there is also a division by 3. So let's do this. So that's 1 over r cubed over 3. And this is plus r prime squared. So it's r squared minus r squared. Is this correct? I think so. And the second one, this is very clear. 2 cancels out, 3 cancels out, r cubed cancels out, which is what we expect, right? Outside the sphere, it's straightforward. It's just 1 over r. It's how far, because we kept the sphere, the origin, that is 1 over r. Inside, let's rewrite this in a certain form. Let me rewrite this, okay, help. This is r squared, 2 by 3 r squared. So this is 2 by 3 minus 1. Right? So that's minus 1 over 3 r squared. So that's r capital R squared minus small r squared over 3. Bring in the 2 by 3 in. So I have 3 by 2 r squared minus of r squared over 2. So that's just simplifying this into just put the free value in. So this expression becomes 4 pi epsilon naught. We keep 1 over r in and the rest of them outside. And this is equal to 3 by 2. So that's 3 by 2 r minus of r squared over 2 r cubed. That's your electric potential inside. Notice the quadratic term that I talked about, that's sitting here. But this constant also sits in there. And again, one can calculate this by saying if we require that the electric potential has to be continuous at the boundary, that's one way of getting this constant. Okay, that's fine. But then derivative of this should be electric field. 1 over capital R. No, it's smaller, right? Observation point. Electric potential due to a sphere is just the observation point, right?
Yeah.
That's the same here, right? But yeah, I think it's correct. Yeah. So electric field is negative gradient of the electric potential, but gradient in spherical coordinates is simply minus r hat times d by partial derivative with r of this function r. So I just have to take a derivative with respect to r. That should be straightforward. This first term is constant, notice, so that gives you 0. First term is 0, and the second term is minus. There's already a minus sign, right? Minus of the minus, that becomes a plus. Then take a derivative, so it's plus 2, and then the 2 cancels out. So it is plus q over 4 pi epsilon naught times r over r cubed. And there's an r hat there, so it's r hat. And that's a linear form you get right away from that. And if you were to take the negative derivative, so there's a negative sign, but the derivative itself has a negative sign. So it is q over 4 pi epsilon naught, 1 over r square r hat. Is that visible? Yeah. So notice that even for a spherical asymmetric system, it involves a good amount of work. And that's why the symmetry, only very symmetric configurations are really doable. But still, we will be able to do a lot of things even with this challenges. And this is the same with gravity also. Like if you had to do a gravitational field due to a let's say two planets, it's not easy. Like one of them you can keep it in the origin and then you can do all this. But the second one you cannot keep it on the origin, right? You don't have choice. So that spoils the whole thing, and that's why you develop functions called legendary polynomials and spherical harmonics. So that we grow often, and we will see a little bit of that. Okay. In your homework, the problem 3 is significantly simpler. You don't have any angular integrals. It's a point object. It's a point dipole actually. So 2 dipoles. So it's a delta function. So that's very straightforward. But still, maybe on Monday, I'll give you some more hints and that might help us. That's all. Thank you. Ah, this goes away outside the screen. Huh? I was not paying attention. Outside the screen. Right, I think whatever I write there, it's just not capturing the whole thing, I think. Right?
Oh, maybe.
I have some.
Maybe it's just because it's not full screen.
Oh, really? You think so?
Maybe, I don't know.
No.
Yeah.
It's okay.
Oh,
I
it's-
think
yeah.
certain things you can just make out, right? Yeah. Seems like they didn't have any problem.